The greatest puzzle in physics is the search for a single, unified law of nature. This quest for a final theory drives some of the most brilliant minds on the planet, and it leads us into realms where mathematics and reality become indistinguishable. One of the most promising paths forward is a concept called supersymmetry, a beautiful symmetry that could elegantly tie together all the forces and particles we know. But to make supersymmetry real within our leading framework, string theory, we need to hide it within the geometry of space itself. This video will give you a clear understanding of the hidden geometric universe that could make supersymmetry, and therefore a unified theory, possible. The mathematics demands that these hidden spaces possess a very special, almost magical property. What is that property, and why does the answer lie in one of the rarest and most exquisite shapes in all of mathematics, known as a G2 manifold? When you think of the building blocks of reality, do you picture geometry? Geometry is the hidden language of the universe, and it speaks most clearly in the smallest of spaces. To understand why, we must shrink our perspective down to the most fundamental level. In string theory, the most basic building blocks of reality are not point-like particles, but tiny, vibrating loops of energy, unimaginably smaller than an atom. The pitch and pattern of a string's vibration determines what kind of particle it becomes, just as the vibration of a guitar string determines the note you hear. A string vibrating one way becomes an electron, another way becomes a photon, the particle of light. This is a profound idea because it means all matter and all forces emerge from geometry and vibration. But there's a catch, a mathematical necessity that opens a door to an extraordinary hidden world. For the equations of string theory to work, these strings must vibrate not just in the 3 dimensions of space we see, but in a total of 10 dimensions. So where are the other 7 dimensions? The answer is a process called compactification. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But up close, you see it has a second dimension, a tiny circular cross-section that wraps around. Our universe could be like that. The familiar 4 dimensions of spacetime, length, width, height, and time, are the long, visible part of the hose. The other 6 or 7 dimensions are curled up into an incredibly small, intricate shape, a shape so tiny that we could never directly perceive it, but whose geometry echoes through everything we can see. This tiny, compact shape is the key to everything. Its exact geometry, its twists and folds and holes, dictates how the strings can vibrate within it. And since those vibrations become particles and forces, the geometry of this hidden space literally writes the laws of physics for our 4-dimensional world. The number of different particle types, their masses, and even the strength of forces like gravity and electromagnetism, all are set in stone by the shape of this invisible 6-dimensional landscape. So the quest for a unified theory becomes a quest in pure geometry. We are searching for the one perfect shape, the one whose geometric song produces the exact symphony of particles and forces we observe in our universe. This hidden shape must sing a very specific tune to give us the universe we know. But how do we listen for that tune? How do we describe the geometry of a space we cannot see? Mathematicians and physicists have a powerful tool for this, a concept that acts like a fingerprint for the shape's deepest nature. It is called holonomy. To grasp it, think of a simple sphere like our planet. Imagine you're standing at the equator, holding an arrow pointing directly north. Now begin walking forward, keeping the arrow pointing in the same direction relative to yourself, never consciously turning it. This careful, step-by-step process of moving a direction without twisting it is called parallel transport. You walk all the way to the North Pole, then turn and follow a line of longitude back down to the equator, and finally walk back along the equator to your starting point. You have completed a giant triangular loop on the curved surface of the sphere. Now look at your arrow. Even though you never intentionally rotated it, the arrow is no longer pointing north. It has been rotated by the journey itself. The curvature of the space, the very shape of the sphere, has imprinted a twist onto your direction. This final rotation, the difference between where your arrow started and where it ended, is the holonomy of that specific loop. Now imagine performing every possible closed loop on that sphere, starting from the same point and moving your arrow in every conceivable way. The collection of all the different rotations you could possibly get forms a mathematical family, a set of symmetries. This family is the holonomy group of the sphere. It is a complete and unique signature of the sphere's curvature. A flat plane has a trivial holonomy group because walking any loop on a flat surface leaves your arrow perfectly unchanged. A more complicated shape, like a donut or an intricate six-dimensional manifold, will have a far richer and more complex holonomy group. This group tells you everything about how the space twists and turns, how it curves back on itself. It is the precise mathematical language for the shape's hidden song. So in our search for the perfect compact shape for string theory, we are not just looking for any six-dimensional space. We are hunting for a shape with a very specific holonomy fingerprint, one whose internal rotations are so special and restrictive that they force the laws of physics in our four-dimensional world to possess the beautiful symmetry of supersymmetry. This concept of holonomy gives us a precise tool for our search. We can now ask, what are all the possible holonomy groups a smooth, curved space can have? It is a question akin to asking what are all the possible types of symmetry a perfect crystal could possess. The answer was a landmark achievement in geometry, a classification completed by the mathematician Marcel Berger. His list reveals a hierarchy of spaces from the ordinary to the extraordinary. At the most general level, you have spaces with the full rotation group. Their geometry is complex and unrestricted, offering no special simplification. Then there are the spaces with reduced holonomy. These are the shapes with extra, built-in symmetry that constrains their geometry, making them far more special and far more useful to physicists. The first major class of these special spaces are the Kepler manifolds with holonomy group U of n. These are complex spaces, meaning they have a built-in notion of multiplication by the square root of -1, which gives them a rich, harmonious structure. They are the natural setting for much of modern geometry. An even more restricted class are the Calabi-Yau manifolds with holonomy group Su of n. These are the legendary shapes that entered popular science through string theory. A Calabi-Yau manifold is a Kepler space that is also Ricci-flat, meaning its curvature is perfectly balanced in a specific way. For decades, these exquisite shapes were the superstar geometries for string compactification, because their special holonomy automatically preserves a lesser version of supersymmetry in the resulting four-dimensional physics. They gave theorists their first concrete glimpse of how hidden geometry could dictate physical law, but the Berger classification held a final, breathtaking tier. Beyond the classical families, his mathematics permitted a handful of exceptional possibilities. These were holonomy groups that did not fit into the familiar infinite series, groups linked to the most rarefied and strange objects in the algebra of symmetries, the exceptional Lie groups. For a six-dimensional space, the relevant exceptional holonomy is called G2. For a seven-dimensional space, it is called spin of 7. These are not just slightly more special than Calabi-Yau manifolds. They represent a different order of geometric refinement altogether. A manifold with G2 holonomy is so constrained, so perfectly symmetrical in its internal structure, that it is one of the rarest and most sought-after objects in all of mathematics. Its existence alone is a deep theorem, and it is this exceptional shape, the G2 manifold, that holds a profound promise. While a Calabi-Yau manifold preserves some supersymmetry, a G2 manifold has the precise, tighter geometric fingerprint needed to preserve a very specific and desirable amount of supersymmetry in 4 dimensions. a key that could unlock a more realistic and stable version of our universe from the equations of string theory. The stage is now set for the main attraction. What does this exceptional holonomy actually do, but what makes a holonomy group exceptional? To answer that, we need to step back into the grand classification of symmetries itself. For over a century, mathematicians have been cataloging the fundamental ways an object can be symmetric, organizing them into families known as Lie groups. Most of these families are infinite, like a vast, orderly library with endless volumes. You have the rotation groups, the special unitary groups, and others, each describing a well-understood type of symmetry that appears everywhere in physics. But at the very edge of this classification, standing apart from the infinite shelves, are 5 singular masterpieces. They are the exceptional Lie groups labeled G2, F4, E6, E7, and E8. These are not part of any infinite family. They are unique, isolated objects of such profound and intricate symmetry that they seem almost like gifts from the mathematical universe, rare jewels with properties that defy easy explanation. They are the outliers, the exceptions that prove the rule is incomplete. Among these 5 rarities, G2 is the smallest and, in a sense, the most tractable. It is the gateway to the exceptional world. While groups like E8 are of monumental size and complexity, G2 is compact enough to study yet still rich enough to contain breathtaking structure. Its remarkable defining property in geometry is this: G2 is precisely the holonomy group of a certain kind of 7-dimensional manifold. This is not a trivial fact. It means that if you want to create a 7-dimensional space whose internal geometry has the unique, exceptional symmetry of G2, that space must be extraordinarily special. Its curvature must be arranged in such a perfectly balanced way that when you parallel transport any direction around any loop, the set of all possible resulting rotations is exactly the G2 group and no larger. This imposes ferocious constraints on the shape. A manifold with G2 holonomy is not just curved, it is curated. Every twist, every fold, every microscopic feature is locked into a harmonious relationship with every other part by the unforgiving demands of this exceptional symmetry. Finding such a shape, or even proving one could exist, was one of the great challenges of modern geometry. This brings us to a crucial pivot in our geometric quest. We have been speaking of 6-dimensional shapes, the Calabi-Yau manifolds, as the traditional setting for string theory. But to reach the exceptional holonomy of G2, we must shift our gaze to a space with one more dimension. Why 7? The answer lies in the ultimate framework that seeks to unify all string theories, a proposal known as M-theory. While the original formulations of string theory required 10 dimensions, M-theory elegantly wraps them into a single, more profound structure living in 11 dimensions. Think of it as the parent theory from which all the different 10-dimensional string theories emerge as different perspectives or limiting cases. This extra dimension is not a minor detail, it is the master key. In this grander picture, our universe emerges from taking the 11 dimensions of M-theory and compactifying 7 of them down into a tiny, complex shape. The 4 large dimensions we experience are what remain. This is why the search for exceptional holonomy becomes a search in 7 dimensions. The internal geometry that matters for the most complete version of our theoretical framework is not 6-dimensional but 7. The properties of this 7-dimensional hidden space, its twists and its holonomy, will directly determine whether the 4-dimensional world we see can host stable matter, the forces we know, and the delicate balance of supersymmetry. So the hunt for the G2 manifold is not a mathematical curiosity. It is a direct consequence of pursuing the most unified version of reality. If M-theory is the blueprint for a final theory, then the 7-dimensional compact space is the foundation upon which our physical universe is built. And the strongest, most stable foundations in geometry are those with exceptional holonomy. This shift from 6 to 7 dimensions is like an architect realizing that the most elegant design requires a specific, rare type of 7-sided crystal as its cornerstone. Everything else in the structure depends on the perfection of that one element. The G2 manifold is that proposed cornerstone, its exceptional symmetry promising to translate the perfect symmetry of the higher dimensional blueprint into the lived-in reality of our world. The rarest spaces in geometry are defined not by what they are made of, but by the invisible symmetry that governs them. A G2 manifold is a 7-dimensional curved space, a shape you could, in principle, navigate in 7 independent directions, though its curvature is tuned to an exquisite standard. Mathematically, it is a Riemannian manifold, meaning it comes equipped with a consistent way to measure distances and angles at every point, much like the surface of a sphere but in many more dimensions. Its defining signature, its geometric fingerprint, is its holonomy. For this space, the holonomy group is contained within, or is exactly equal to, the exceptional Lie group G2. This single condition is a constraint of immense power. It means every possible twist imparted by the curvature, every rotation you could experience by traveling any loop in this 7-dimensional landscape, respects the unique, exceptional symmetry patterns of G2. Nothing is arbitrary. The space cannot have just any curvature. It must have a curvature perfectly orchestrated to sing only the notes allowed by this exceptional group. There is a profoundly beautiful and equivalent way to understand this condition. It all centers on the existence of a very special object living on the manifold, a mathematical entity known as a differential form. In our 3-dimensional world, we are familiar with forms that measure volumes. A differential form is a more sophisticated tool that allows mathematicians to measure oriented volumes in higher dimensions, to integrate over curves, surfaces, and their higher dimensional analogues. On a potential G2 manifold, there must exist one particular, globally defined differential form of a specific type. Think of this form not as a mere measurement, but as the soul of the manifold's geometry. It is called the G2 structure. This form does not just exist, it is harmoniously integrated into the very fabric of the space. The technical condition is that this special form is covariantly constant. In plain language, this means the form is perfectly aligned and unchanging with respect to the manifold's own innate sense of parallel transport. If you were to pick up this geometric soul at one point and carefully carry it without twisting along any path to any other point in the 7-dimensional shape, it would arrive looking exactly the same. It is a global constant, a unified field of geometric information that stamps the entire space with the exceptional G2 pattern. This is why finding such a manifold is so difficult. You are not just sculpting a 7-dimensional shape, you are searching for a shape that can host this perfectly rigid, globally consistent geometric object. The existence of this covariantly constant G2 structure and the condition of G2 holonomy are two sides of the same coin. They are different languages describing the same ultimate reality, a space of such refined internal harmony that it forces a specific, exceptional symmetry onto every physical process that could occur within it. This is the pristine geometric foundation that theorists believe could support our universe. This special 3 form is the master key that locks the geometry into its exceptional state. To understand its power, we must first grasp what a differential form represents. In our familiar 3-dimensional world, we have a natural tool for measuring volume. A differential form is the higher dimensional generalization of this idea. It is a mathematical object that allows you to measure oriented volumes not just of 3-dimensional regions, but of curves, surfaces, and their exotic analogues in 7 dimensions. On a potential G2 manifold, there exists one particular 3 form, universally denoted by the Greek letter phi, that is not just present, but is perfectly integrated into the fabric of the space. This phi is not a number, it is a field. Imagine it as a unique geometric weather that permeates every single point of the seven-dimensional landscape. At each location, this phi form defines a specific way of measuring a certain kind of oriented three-dimensional volume. Its existence is what gives the manifold its G2 structure. But for the space to achieve the coveted G2 holonomy, this phi field must be extraordinarily special. It must be covariantly constant. What does that mean in human terms? Think of phi as a delicate, three-dimensional geometric template, like a perfectly calibrated gyroscope. If you were to pick up this template at one point, and then carefully carry it along any path through the curved manifold, moving it in the way the curvature itself dictates without adding any extra twist, this template would arrive at its destination completely unchanged. It remains perfectly aligned with itself no matter where you go. This is a condition of breathtaking rigidity. The entire seven-dimensional shape must be curved in exactly the right way to allow this globally consistent, unchanging field to exist. It is as if the entire universe had to be sculpted to accommodate a single, unvarying idea. This condition is so powerful that it alone forces the holonomy group to be contained within G2. The presence of this constant three-form strangles the geometric possibilities, eliminating any arbitrary twists or turns that would break the exceptional symmetry. To use a simpler analogy, consider a symplectic form, which is the key structure in a different class of special manifolds. A symplectic form essentially provides a consistent way to measure area for every two-dimensional slice within a space, imposing a kind of geometric harmony. The G2 three-form phi is like a vastly more sophisticated version of this. It doesn't just measure area, it defines a specific, rich notion of three-dimensional volume that intertwines the seven directions in a highly non-trivial way. Its constancy forces this intricate volumetric relationship to hold true everywhere, weaving the entire space into a single, coherent geometric tapestry. This is why finding explicit examples of these manifolds is a monumental challenge. You are not merely looking for a curved space, you are hunting for a space that can host this perfectly rigid, self-consistent geometric field. The three-form phi is both the architect and the blueprint, dictating every contour of the hidden universe it inhabits. This rigid geometric harmony is not an abstract pursuit, it is a direct response to a profound physical demand. The entire reason we are searching for these exquisitely constrained shapes comes from a deep need within our theories of nature, a principle called supersymmetry. You can think of supersymmetry as the ultimate cosmic partnership, a proposed symmetry that would pair every known particle of matter, like quarks and electrons, with a superpartner force-carrying particle, and pair every known force particle, like photons, with a superpartner matter particle. It is a beautiful, doubling symmetry that would elegantly solve several of the deepest puzzles in fundamental physics, from the stability of the Higgs boson's mass to the nature of the universe's unseen dark matter. But for this symmetry to be a real feature of our four-dimensional world, it must survive the journey down from the higher dimensions. When we compactify the extra dimensions of string theory or M-theory, we are essentially projecting a 10 or 11-dimensional reality onto our four-dimensional one. This projection can easily break delicate symmetries, just as squashing a perfectly symmetrical snowflake under glass might destroy its intricate patterns. The physical demand, then, is for a compactification that preserves supersymmetry. What does that mean in practical terms? In the higher dimensional theory, there exist mathematical operators called supercharges. These are the generators of supersymmetry, the entities that would transform an electron into its superpartner and back again. For supersymmetry to remain a feature of our everyday physics, at least some of these supercharges must remain valid, unbroken symmetries after the compactification process. They must find a way to exist consistently within the twisted geometry of the tiny, hidden space. This is where geometry and physics perform a breathtaking duet. There is a critical, powerful theorem that provides the bridge. It states with mathematical certainty that for a compactification to preserve a minimal amount of supersymmetry in the resulting four-dimensional universe, the internal manifold, the shape of the hidden dimensions, must have reduced holonomy. It cannot have the full generic rotation group. Its holonomy group must be a proper subgroup, a smaller, more specialized set of rotations. Why is this the case? Remember the connection between holonomy and parallel transport. The holonomy group tells you how directions, and by extension how more complex objects like spinors, which are the mathematical descriptions of fundamental particles, get rotated as they move through the curved space. If the holonomy group is too large, if the internal space twists things in too many arbitrary ways, it will inevitably rotate a supercharge into something else, breaking the symmetry. It will destroy the snowflake, but if the holonomy is reduced, it means the space has built-in constraints on how it can rotate things. There are certain directions or spinorial properties that remain unchanged, that are immune to the twisting of the geometry. These invariant quantities are the candidates for the unbroken supercharges. The more the holonomy is reduced, the more supersymmetry you can potentially preserve. A Calabi-Yau manifold with its SU of 3 holonomy preserves a quarter of the original supersymmetry. This was a major victory, but for the most realistic and stable physical models, theorists often seek an even more minimal preservation, a single, unbroken supercharge. And this leads us to the pinnacle of the classification. To preserve this minimal, most desirable amount of supersymmetry from M-theory, the theorem points unequivocally to the most restricted holonomy possible for a 7-dimensional space. The internal manifold's geometry must be so tightly controlled that its holonomy group is not just reduced but exceptional. It must be contained within G2. In this space of exceptional holonomy, the curvature is so perfectly tuned that it allows exactly the right spinorial objects to remain constant as they are parallel transported everywhere. These invariant spinors become the single, unbroken supercharge in our 4-dimensional world. So the hunt for the G2 manifold is not a mathematician's hobby. It is a direct, non-negotiable consequence of the demand for a stable, supersymmetric universe. The physical need writes a geometric prescription, and the prescription calls for the rarest ingredient in the mathematical cosmos. The journey to G2 holonomy was paved by an earlier, revolutionary discovery. For decades, the dominant geometric template for string theory was not a 7-dimensional shape, but a 6-dimensional one, known as a Calabi-Yau manifold. These spaces, with their holonomy in the special unitary group SU of 3, became the first great hope for connecting hidden geometry to our physical world. Their story is a testament to the power of mathematical beauty in physics. The appeal of Calabi-Yau manifolds was immediate and profound. Their special holonomy guaranteed that when you used them to compactify the 6 extra dimensions of a particular version of string theory, called heterotic string theory, the resulting 4-dimensional universe would automatically possess a significant amount of supersymmetry. It was a perfect match, a geometric key that neatly turned in the theoretical lock. This discovery unleashed a golden age of exploration. Physicists and mathematicians worked together to probe the properties of these shapes, calculating how their intricate topologies, the numbers of holes and handles in various dimensions, would translate into specific particle physics phenomena. Each distinct Calabi-Yau manifold represented a different possible vacuum, a different set of laws for a potential universe. This led to the famous notion of the string theory landscape, a vast, perhaps infinite, collection of possible geometric settings, each with its own particle content and force strength. The Calabi-Yau paradigm was wildly successful in demonstrating the core principle that geometry dictates physics. It showed that the search for a unified theory could be transformed into a concrete, if immensely complex, problem in pure mathematics. We learned that the number of generations of matter particles in such a universe could be tied directly to a simple topological number of the Calabi-Yau shape. an astonishing connection between the abstract and the tangible. Yet, for all its triumphs, this approach revealed inherent limitations. The heterotic string theories compactified on Calabi-Yau manifolds are what physicists call perturbative descriptions. They are excellent at describing interactions when strings are weakly coupled, behaving like gentle, non-interacting threads, but they struggle to capture the full, rich physics when the interactions become strong, a regime known as non-perturbative. It is like having a detailed map of a coastline but no understanding of the powerful, churning ocean currents just beyond the shore. This is where M-theory enters, proposing a deeper, 11-dimensional framework that unifies all string theories and naturally incorporates these strong coupling effects. And here, the 6-dimensional Calabi-Yau shape is no longer sufficient. The compact space required by M-theory is 7-dimensional. The physics we seek to describe, the full non-perturbative tapestry that includes objects like membranes and instantons, demands a new kind of geometric foundation. The Calabi-Yau manifolds were the brilliant pioneers, proving the land was fertile, but to build the ultimate unified home, we need to work with a different, more robust material. That material is the 7-dimensional space with exceptional holonomy. So while we honor the Calabi-Yau precedent for opening the door, we now stand at the threshold of a new architectural challenge, one that requires the unique strength and symmetry of G2. This physical demand creates a mathematical mandate of absolute clarity. The bridge between the 11-dimensional elegance of M-theory and the 4-dimensional world we inhabit is not a matter of preference, it is a matter of precise, unbreakable geometric law. Here is the core argument, a statement of such definitive power that it shapes the entire modern search for a unified universe. When you take the full framework of M-theory with its 11 dimensions and you compactify 7 of them down into a tiny, curled-up shape, the resulting physics in our large 4 dimensions will possess a specific minimal amount of supersymmetry, known as n equals 1. If and only if the internal 7-dimensional space has G2 holonomy. This is not a suggestion, it is a theorem. The words if and only if are the keystone. They establish a perfect two-way logical lock between a condition in physics and a condition in geometry. On one side, you have the physical requirement, n equals 1 supersymmetry in 4 dimensions. This is the most desirable and realistic amount for constructing particle physics models that resemble our own. It provides just enough of the symmetry's benefits, like stabilizing the Higgs mass and offering a dark matter candidate, without predicting phenomena we do not observe. On the other side, you have the geometric fingerprint G2 holonomy. The theorem states these are equivalent. You cannot have one without the other. If you desire that specific, minimal supersymmetry in your 4-dimensional world, then you are compelled, by the iron logic of the equations, to compactify on a 7-dimensional manifold whose curvature is so exquisitely constrained that its holonomy group is G2. Conversely, if you succeed in constructing such a manifold and use it for compactification, the resulting physics is guaranteed to possess that precious n equals 1 supersymmetry. This transforms the search from an open-ended exploration into a targeted mission. For theorists building realistic models within the most complete version of our unified framework, G2 manifolds are not just interesting possibilities, they are the central objects, the non-negotiable foundation. All other geometric options, spaces with more generic holonomy, would completely break the supersymmetry, leaving a 4-dimensional world that looks nothing like our own, likely unstable and devoid of the delicate structures that allow for complex matter. Think of it as a filter of cosmic proportions. The universe, through the mathematics of M-theory, imposes a filter that only allows spaces of exceptional holonomy to transmit a stable, life-friendly set of physical laws into the macroscopic realm. Any hidden shape that does not meet this exceptional standard is filtered out, representing a possible universe that either collapsed immediately or never developed structure. So the pursuit of G2 geometry is far more than abstract mathematics. It is the direct consequence of asking for a universe that can last long enough and be stable enough for us to be here to ask the question. The mandate is clear: to build a realistic world from M-theory, you must first learn to build with the rarest geometric material in existence. The geometry of that hidden 7-dimensional space writes the laws of our universe in a language we are only beginning to translate. When we compactify M-theory on a G2 manifold, the exceptional symmetry of the shape acts like a cosmic translator, converting its pristine 11-dimensional rules into the 4-dimensional physics we might one day observe. The first and most fundamental things to emerge are fields not of force but of shape. These are the moduli. Think of the G2 manifold not as a rigid statue but as a breathing, living shape. It can be deformed in certain ways without breaking its exceptional holonomy. Much like a perfectly tuned bell can be made slightly larger or smaller while still ringing the same pure note. Each of these allowed deformations, each independent way the internal geometry can breathe, gives rise to a massless scalar field in our 4-dimensional world. We call these moduli fields. They are like the dials and tuning knobs of the universe, parameters that in principle could determine things like the strength of forces or the size of the compact dimensions themselves. Among these moduli, a special class arises from deformations that are closely tied to the special 3 form, phi, that defines the G2 structure. Some of these fields behave in a particularly interesting way, acquiring a kind of periodic symmetry. In the language of particle physics, we call these axions. They are hypothetical particles that are leading candidates for the mysterious dark matter that fills our cosmos. So from the very act of allowing the hidden shape to flex, we get potential ingredients for the universe's most elusive substance. But matter and forces as we know them require more than just shape-shifting fields. They require charged particles and the gauge fields that mediate their interactions, like the photon for electromagnetism. This is where the flawless perfection of a smooth G2 manifold meets the creative power of imperfection. To get realistic physics, we must introduce singularities into the geometry. A singularity in this context is not a black hole's crushing-in point, but a precise, localized flaw in the fabric of the 7-dimensional space, a place where the smooth mathematical description breaks down in a controlled way. Imagine the G2 manifold as a vast crystal lattice. A singularity is like a defect in that crystal, a place where the orderly pattern is disrupted. And just as defects in a real crystal can trap electrons, these geometric defects can trap the fundamental objects of M-theory. Specifically, they can localize membranes. When these higher dimensional membranes wrap around cycles, which are non-trivial loops or surfaces associated with the singularity, they manifest in our 4-dimensional perspective as particles. Crucially, the way these membranes interact near the singularity can generate the mathematical structure of a gauge theory. The singularity itself defines the symmetry group, like SU of 3 or SU of 5, and the wrapped membranes provide the charged particles, the quarks and leptons, that feel that force. This is a profound insight that the forces which bind our world could literally be the shadows cast by the twisted geometry of the hidden dimensions. The final, crucial ingredient for our universe is chirality. This is the property that distinguishes left from right in the world of fundamental particles, a fundamental asymmetry that is baked into the standard model of particle physics. Our world is chiral. For example, neutrinos only spin in a left-handed orientation relative to their motion. A major challenge for any unified theory is to generate this handedness naturally. Remarkably, G2 compactifications can do this. The singularities that give rise to gauge fields and charged particles do not exist in isolation. They can be of a particular type that, when analyzed, leads to chiral fermions, the handed matter particles we know. The mathematics reveals that the number of generations of these particles, like the 3 families of quarks and leptons, is tied directly to topological invariance of the singularity structure. It is a numbers game played out in the geometry of the defect. So from the controlled imperfections within a space of exceptional holonomy, we can in principle derive the full spectrum, the forces, the matter, and even its intrinsic left-right asymmetry. The resulting four-dimensional theory from such a compactification is a potent candidate for reality. An n=1 supersymmetric gauge theory with chiral fermions, moduli that could become dark matter, and a direct geometric origin for every element. It is a universe in waiting, written in the silent, curved language of 7 dimensions. The mathematical mandate is clear, yet fulfilling it has proven to be one of the most daunting challenges in modern science. We know exactly what we need, a compact 7-dimensional space with G2 holonomy, but actually building one, writing down its explicit metric and proving it possesses that exceptional symmetry is an endeavor of staggering difficulty. This stands in stark contrast to the earlier generation of special shapes, the Calabi-Yau manifolds. For those 6-dimensional spaces, mathematicians have discovered entire galaxies of examples. Using the powerful tools of algebraic geometry, which describes shapes as solutions to polynomial equations, they have constructed literally millions of distinct Calabi-Yau manifolds, cataloging them in vast databases. This abundance provided physicists with a rich landscape to explore, even if it led to the famous problem of too many choices. For G2 manifolds, the situation is reversed. We face a profound scarcity. There is no known algebraic construction that directly yields a smooth, compact G2 manifold. They exist in a different mathematical realm, one that resists the equation-based approaches that worked so well for their 6-dimensional cousins. This means we cannot simply write down a set of equations and solve them to get an example. Instead, mathematicians and physicists must become cosmic architects, piecing these rare spaces together from simpler, more understandable components through ingenious and often indirect methods. The primary strategy is one of geometric surgery. The idea is to start with a simpler, non-compact space that we understand well, often one that has a singularity or a boundary, and then carefully glue it to another piece or to itself in a clever way to produce a closed, compact shape. It is like taking two intricate, open-ended crystal structures and fusing their edges together with such perfect precision that the resulting object is seamless and retains the exceptional internal symmetry. One famous example of this is the construction of a G2 manifold by taking two simpler 7-dimensional spaces, each with a conical singularity, and gluing them together along their singular tips. When done with exacting care, the singularities cancel out, and you are left with a smooth, compact manifold whose holonomy is exactly G2. Another approach is to work in the limit, studying families of spaces that degenerate or become singular in a controlled way. By deeply understanding the structure of these singular limits, mathematicians can sometimes prove that a smooth, compact G2 manifold must exist in a nearby, non-singular region of the family, even if they cannot write down its exact form. This is akin to knowing that a perfect, unblemished gem must exist within a certain vein of rock because you have meticulously studied the flawed crystals surrounding it. These constructions are monumental achievements, each one a hard-won victory that expands our library of known examples from a handful to a slightly larger handful. They represent the cutting edge where advanced differential geometry, topology, and theoretical physics converge. The search for explicit G2 metrics is not just an abstract puzzle, it is a major frontier. Without a large pool of examples to study, physicists cannot fully explore the cosmological implications of these spaces. They cannot systematically calculate particle spectra or model the evolution of the moduli fields that might become dark matter. Every new example that is constructed or proven to exist provides a new laboratory, a new set of geometric conditions from which a potential universe could emerge. So while the Calabi-Yau era was marked by an embarrassment of riches, the G2 era is defined by a painstaking search for treasure, where each new discovery reshapes our understanding of what is possible in the hidden dimensions of reality. Dominic Joyce provided the definitive answer to a question haunting mathematicians for decades. Could a smooth, compact seven-dimensional space with G2 holonomy actually be built, or was it merely a beautiful phantom of theory? In the 1990s, Joyce achieved what many thought might be impossible. He constructed not one, but several explicit examples of these elusive manifolds. His landmark work was a masterclass in geometric engineering, a meticulous process of building perfection from controlled imperfection. He began not with a smooth shape, but with something far simpler and more chaotic, a seven-dimensional torus orbifold. Imagine a perfect, flat seven-dimensional cube, but with a twist, literally. An orbifold is what you get when you take such a shape and identify its points under a discrete set of rotations, essentially folding it onto itself according to a strict symmetry rule. This folding creates singularities, sharp, pinched points where the smooth geometry breaks down. Think of taking a flat piece of paper and folding it sharply to create a crease. The crease line is a singularity in the two-dimensional surface. Joyce's starting torus orbifold was riddled with such creases and pinch points, a jagged, non-smooth space that was easy to describe mathematically but physically unacceptable, as its singularities would break the very supersymmetry we seek. The brilliance of the construction lay in the next step, resolution. Joyce developed a systematic procedure to carefully blow up each singularity, replacing each sharp crease and pinch point with a tiny, smooth geometric patch. This is not random smoothing, it is a precise surgical technique. Each type of singularity in the orbifold has a known, canonical way to resolve it into a smooth manifold. The challenge was to perform this surgery at every singular point simultaneously, ensuring that all the new smooth patches glued together perfectly across the entire seven-dimensional space. It is like taking a complex, fractured crystal and with microscopic tools replacing every flawed region with a perfect, strain-free piece of gemstone, so seamlessly that the final object appears to have grown that way naturally. The monumental achievement was proving that after this entire delicate operation, the resulting stitched together, now perfectly smooth manifold retained the essential property. Its curvature was so exquisitely balanced by the resolution process that its holonomy group was exactly G2. Joyce did not just wave his hands, he provided the explicit, albeit complicated, Riemannian metric for these spaces, the actual mathematical formula defining distances and angles at every point. This was the concrete proof the field needed. These were not just abstract existence theorems, they were blueprints. The Joyce constructions demonstrated irrefutably that these rarest of geometric spaces were not just figments of the imagination, but robust, buildable objects in the landscape of mathematics. They transformed G2 manifolds from a tantalizing possibility into a solid, foundational reality for physicists to use. Every subsequent exploration of phenomenology from M-theory compactification rests upon the certainty that Joyce provided. The certainty that the universe's most perfect hidden geometry can, in fact, be built. The very geometry that could define our universe also holds a key to its greatest mystery. We have seen how a G2 manifold can shape particles and forces, but its deepest influence may be on the very fabric of spacetime itself, through a single number of profound importance, the cosmological constant. This is the energy density of empty space, a kind of background hum to the cosmos. Its observed value is incredibly small and positive, causing the expansion of our universe to accelerate ever so slightly. Yet, our fundamental theories, when asked to calculate this number from first principles, predict a value larger by a staggering 120 orders of magnitude, a number so immense it would have ripped the universe apart in an instant. This colossal mismatch is the cosmological constant problem, arguably the most severe disconnect between theory and observation in all of physics. The geometry of hidden dimensions may offer a path through this impasse. When we compactify M theory on a G2 manifold, we do not get a single, unique four-dimensional universe. Instead, we get a vast landscape of possibilities. Each distinct G2 manifold represents one possible vacuum state, one set of physical laws. But even within a single manifold, there is not one rigid configuration. Remember the moduli fields, the ways the internal shape can breathe while preserving its exceptional holonomy. These moduli represent continuous parameters, dials that can be turned. In a full quantum treatment, however, these continuous parameters get quantized. The breathing modes become frozen at discrete, distinct values. Each choice for how all these moduli are fixed corresponds to a specific, stable vacuum with a specific value for the vacuum energy, the four-dimensional cosmological constant. The result is not a single prediction but a vast discretuum, a densely spaced but discrete spectrum of possible values for this fundamental constant. Imagine a cosmic piano with an astronomical number of keys, each key representing a possible vacuum with a specific cosmological constant. Most of these keys, when struck, produce a deafening, universe-shattering note, a value of vacuum energy so large it would prevent any structure from ever forming. But scattered across this immense keyboard are a tiny, rare few keys that produce an almost silent whisper, the tiny, positive value we observe. This is where the geometry of G2 manifolds intersects with a powerful, if controversial, line of reasoning, the anthropic principle. The argument is straightforward. If the landscape of vacua from string theory and M theory is real and vast, then all these different universes, with all their different physical constants, are in some sense realized. We, as conscious observers, can only find ourselves in one of the exceedingly rare universes where the cosmological constant is small enough to allow galaxies, stars, planets, and ultimately, life to evolve. We do not observe the typical, catastrophic value because in those universes, no one is there to observe anything. The exceptional holonomy of the G2 manifold provides the precise geometric mechanism to generate this landscape. Its moduli, frozen by quantum effects, create the discrete set of tuning forks that determine the background energy of spacetime. So, the astonishing smallness of the cosmological constant may not be a problem to be solved by a single, elegant equation, but a selection effect, a consequence of our existence within a multiverse of geometric possibilities. The quiet hum of our expanding cosmos might be the direct echo of a specific, finely tuned breath taken by a seven-dimensional shape of exceptional symmetry. The silent geometry of a G2 manifold does more than just whisper the cosmological constant. It can shout the entire roster of particles that make up our world. To understand how, we must look not at its smooth perfection, but at its deliberate, controlled flaws. The pathway to a realistic universe like our own lies in the strategic placement of singularities within the seven-dimensional space. These are not the catastrophic singularities of black holes, but precise, conical defects in the fabric of the manifold, places where the geometry pinches down to a point in a very specific, mathematically tame way. It is at these singular points that the magic of particle creation happens. When the manifold develops such a conical singularity, the local geometry near that defect changes dramatically. The smooth, featureless curvature of the pure G2 space is replaced by a more structured pattern. This local pattern possesses its own enhanced symmetry. Remarkably, this localized symmetry is mathematically identical to a non-abelian gauge group. To grasp this, think of the singularity as a kind of geometric lens. The pristine G2 holonomy around it acts like a filter, but right at the defect, the filtering breaks down in a perfectly symmetrical manner, allowing a specific set of rotational symmetries to emerge. These are the same symmetries that define forces like the strong nuclear force, which is based on the group SU of 3, or the unified electroweak force. So, a single conical defect in the seven-dimensional shape can literally give birth to an entire force field in our four-dimensional perspective. The singularity is not the force itself, but the geometric seed from which the force gauge fields grow, localized in the extra dimensions but felt everywhere in our four-dimensional spacetime. This is how the strong force, with its 8 gluons, could have a purely geometric origin, woven into the very folds of the hidden dimensions. But forces alone are not enough. We need the particles that feel those forces, the quarks and leptons that make up atoms and ultimately us. This requires a second brilliant feat of geometric engineering. The particles, the chiral fermions, do not come from the singularities themselves, but from how the fundamental objects of M-theory interact with them. In M-theory, there exist two-dimensional membranes. When the seven-dimensional space contains a conical singularity, these membranes can wrap around specific cycles, which are non-contractible loops or surfaces associated with the defect. Imagine a tiny, elastic loop settling around the narrow throat of the singularity. This wrapped membrane, from our four-dimensional viewpoint, no longer looks like a two-dimensional sheet. Its vibrational modes along our large dimensions behave exactly like a point particle, and because it is wrapped in a specific way around a geometric feature tied to a gauge symmetry, this particle automatically carries the correct charge under that force. It becomes a quark that feels the strong force or an electron that feels electromagnetism. Even more crucially, the geometry of the singularity and the way the membrane wraps can break the symmetry between left and right in just the right manner to produce chiral fermions, the handed particles that are the hallmark of our physical reality. The number of generations of these particles, the three families we observe, is then determined by topological invariance of the singularity structure, essentially counting the number of distinct, stable ways these membranes can wrap. So, from the interplay between controlled geometric flaws and vibrating membranes, we get the entire particle content of a theory like the minimal supersymmetric standard model. Every force carrier and every matter particle finds its origin in a specific feature of the seven-dimensional landscape. The universe is not just written in geometry, it is written in the precise, localized grammar of singularities and cycles, a cosmic code where every particle is a syllable spoken by the shape of hidden space. Yet this beautiful geometric origin for particles and forces presents us with a profound and urgent problem. All those moduli fields, the breathing modes of the G2 manifold that could become dark matter, have a dangerous side. In their natural, massless state, they would wreak havoc on our universe. A massless scalar field is a ghostly entity that interacts very weakly with matter, but its presence would have observable consequences we simply do not see. It would mediate a new, long-range fifth force, altering the orbits of planets and the behavior of atoms in ways that have been definitively ruled out by experiment. Furthermore, these massless fields represent flat directions in the landscape of possibilities, meaning the universe could easily roll from one vacuum to another, changing the very laws of physics over time. Our cosmos is stable and its laws are constant, so these moduli cannot remain as free, massless parameters. They must be pinned down, frozen into place, and given a substantial mass. This is the central challenge of moduli stabilization, and solving it is the critical step in turning a beautiful mathematical construction into a viable physical reality. The process of stabilization is like taking that perfectly tuned, breathing bell and carefully embedding it within a block of crystal. We must find mechanisms to lock the shape, to give stiffness to its deformations, without shattering the exceptional holonomy that makes it special in the first place. Fortunately, the toolbox of M-theory provides two powerful instruments for this task, and they often must work in concert. The first instrument involves threading the hidden dimensions with fluxes. Think of a flux as a background field strength akin to a magnetic field, but one that permeates the higher dimensional space. In M-theory, we have not just the familiar electromagnetic field, but a three-form field often called the C field. We can turn on a background value for this field, meaning we allow it to have a specific fixed strength that wraps around certain cycles within the G2 manifold. It is like weaving invisible threads of energy through the holes and handles of the seven-dimensional shape. This act of turning on fluxes has a direct physical effect. It generates a potential energy landscape for the moduli fields. The potential is like a complex, hilly terrain. Each point on this terrain corresponds to a specific configuration of the moduli, a specific way the internal geometry is deformed. The fluxes sculpt this terrain, creating valleys and wells. A moduli field sitting at the bottom of a deep well is stabilized. It has a minimum energy and a mass proportional to the steepness of the walls of the well. It can no longer wander freely. The challenge is to use fluxes to create a well for every single modulus, locking down every possible deformation of the internal space. But fluxes alone may not be enough to create a deep, stable well for all moduli, particularly for those associated with the overall volume of the manifold. This is where the second, more subtle instrument comes into play: non-perturbative effects. These are quantum processes that are inherently tied to the strong coupling regime, effects that cannot be seen by approximating interactions as weak and gentle. The most important of these for G2 compactifications are gauge theory instantons. Recall that the conical singularities within the manifold give rise to non-abelian gauge theories like the strong force. In such theories, an instanton is a special, localized quantum tunneling event, a brief fluctuation in the gauge field that has a specific topological character. It is a tiny, ephemeral bubble of twisted field lines. In the context of the compactified space, these instantons, when they occur within the gauge theory living on a singularity, can generate additional contributions to the potential energy for the moduli. Specifically, they can depend exponentially on certain moduli like the overall volume. This exponential dependence is crucial because it can create a steep, deep minimum where a flux-generated potential might only create a shallow slope. It is the difference between a gently rolling hill and a narrow, canyon-like crevasse. The instanton effect provides the sharp, defining walls that can firmly trap a modulus. The ultimate goal, then, is a combined assault. We must thread the G2 manifold with a specific pattern of fluxes and rely on the non-perturbative magic of instantons from its gauge theory sectors to sculpt a potential energy landscape with a single, isolated, deep minimum. In this minimum, every modulus is fixed, every breathing mode is frozen, and the entire seven-dimensional geometry is rigidly locked into one specific, stable configuration. Only when this Herculean task is achieved does the compactification yield a four-dimensional universe with a fixed, finite cosmological constant and massive, hidden moduli that could perhaps later decay into the dark matter we observe. The search for such fully stabilized vacua is the grand, unfinished work at the heart of connecting exceptional geometry to our exceptional reality. The mathematical elegance of G2 manifolds meets a very modern, pragmatic reality. While the existence proofs and intricate constructions are triumphs of pure thought, they often leave a crucial question unanswered for the physicist: what are the actual numbers? If we want to calculate the mass of a predicted particle, the strength of a force, or the precise value of the cosmological constant from a specific G2 compactification, we need more than a proof of existence. We need the actual metric, the detailed map of distances and curvatures at every point in that seven-dimensional space. For all but the simplest, most symmetric examples, writing down such a metric with pen and paper is a task beyond human capability. The defining equations are a ferociously complex set of non-linear partial differential equations. This is where the quest shifts from the realm of pure abstraction to the domain of silicon and algorithms, giving rise to a numerical revolution in geometry. Faced with equations that cannot be solved by hand, researchers have turned to a powerful alternative: they approximate. The strategy is to discretize the manifold, to represent this smooth, continuous seven-dimensional shape as a vast collection of discrete points or a mesh connected in a specific way. Think of it like creating a digital sculpture of an impossibly complex organic form. You start with a wireframe model made of countless tiny, interconnected seven-dimensional simplices, which are the higher-dimensional analogues of triangles and tetrahedra. This mesh is not the true, smooth manifold, but it can be made to approximate it with arbitrary precision by using more and more finer and finer points. The goal of the computation is then to adjust this digital mesh, to make it sag and bend in its abstract, high-dimensional space until it satisfies as closely as possible the defining equations for a G2 structure. It is a process of geometric evolution by brute force calculation. This is not a task for a desktop computer. The number of variables involved, representing the positions and connections of all those mesh points in 7 dimensions, is astronomical. Solving the system requires the raw power of supercomputers, running for days or weeks on thousands of processors in parallel. The algorithms work iteratively, making small adjustments to the simulated geometry, checking how well it fits the G2 conditions, and then adjusting again in a relentless digital pursuit of exceptional holonomy. It is a computational alchemy attempting to transmute a rough, discrete lattice into a perfect, curved geometric jewel. What emerges from these monumental calculations is a new kind of insight. Once the computer has converged on a stable numerical solution, it holds a complete point-by-point description of the approximated G2 metric. From this data, physicists can then extract the physical quantities they crave. They can compute the spectrum of low-energy particles, the four-dimensional effective potential that governs the moduli fields, and the couplings that determine how those particles interact. For the first time, it allows for the exploration of specific, concrete universes emerging from G2 compactification, moving beyond general arguments to testable numerical predictions. This numerical frontier is transforming the field from a study of beautiful possibilities into a workshop for building quantitative models of reality, one supercomputer cycle at a time. The hidden geometry that could shape our cosmos also resonates in the laboratories here on Earth. This is the surprising truth about advanced mathematics. Its patterns echo across the universe of ideas, appearing in realms that seem, at first glance, completely disconnected from string theory or particle physics. One of the most vibrant of these realms is the study of condensed matter, the physics of solids and liquids, of superconductors and exotic materials. Here, researchers are not probing the fabric of spacetime, but the collective dance of billions upon billions of electrons in a carefully crafted crystal. Yet, in the quantum choreography of these systems, the same elegant structures emerge. The mathematical language developed to understand G2 manifolds, particularly the theory of three forms and exceptional holonomy, finds a powerful application in classifying some of the most bizarre states of matter ever discovered. These are the topological phases. Imagine a material not defined by what it is made of, but by the global, untouchable shape of the quantum wave functions of its electrons. This shape is so robust that you can deform the material, introduce impurities, or even change its temperature slightly, and the essential quantum order remains unbroken. It is a state of matter protected by topology, the same mathematics that describes why a coffee mug and a donut are fundamentally the same, because each has one hole. In 3 spatial dimensions, describing and classifying these exotic topological phases becomes a monumental challenge. This is where the connection crystallizes. The theoretical tools used to pin down these phases are often 3-dimensional topological field theories. These are simplified but profoundly deep models that capture the universal, shape-dependent properties of the quantum system, filtering out all the messy microscopic details. And within the zoo of possible 3-dimensional topological field theories, certain classes are intimately related to the geometry of G2 structures. The same mathematical constraints that force a 7-dimensional space to have exceptional holonomy can be used to define and categorize a particular family of these topological theories. In practice, this means a physicist studying a strange new crystal in a lab could, in principle, use the classification theorems from advanced geometry to identify what kind of topological phase they have created. The G2 structure acts as a kind of cosmic filing cabinet, providing a slot for a specific type of quantum order in our 3-dimensional world. This is a stunning demonstration of the unifying power of pure mathematics. A set of ideas born from the quest to unify gravity and quantum mechanics to describe the birth of the universe turns out to provide the perfect vocabulary for describing the behavior of electrons in a man-made material cooled to near absolute zero. It tells us that the geometry of exceptional holonomy is not just about the hidden dimensions of reality. It is about a deeper, more fundamental pattern of organization that can manifest at vastly different scales. Whether in the curled-up dimensions of a unified theory or in the entangled heart of a quantum material, the same exquisite mathematical symmetry can govern the rules of the game. This cross-pollination is a powerful engine for discovery. Insights from the abstract world of string compactification can suggest new types of topological order to search for in the lab. Conversely, the strange behavior of electrons in these materials can inspire new ways to think about the moduli fields and singularities in our geometric models of the universe. It reveals a single, beautiful tapestry of understanding, where threads from the largest questions and the smallest experiments are woven together by the common language of shape and symmetry. The pristine perfection of a full G2 holonomy is a breathtaking ideal, but our universe is not a place of perfect, frozen symmetry. It is a dynamic, evolving reality with a small but positive energy humming in its empty spaces. To reach that realistic state, we must sometimes step back from the most rarefied geometric ideal. This brings us to a broader, more flexible, and ultimately more useful class of shapes known as G2 structures. Until now, we have spoken of G2 manifolds as spaces that possess both a special 3-form, phi, and the condition that this form is covariantly constant, leading directly to the exceptional holonomy. But what if we relax that second, most stringent requirement? Imagine a 7-dimensional space that still has that special phi form woven into its fabric at every point, giving it a local G2 symmetry, but we no longer demand that phi be perfectly constant as we move around. We allow it to twist and strain slightly as it is parallel transported. This space still has a G2 structure, but it is a structure with torsion. Torsion, in this geometric sense, is a measure of the failure of the 3-form to be constant. It quantifies the internal stress within the geometry, the slight misalignment that occurs when you carry the phi template from one point to another. A space with a G2 structure but non-zero torsion does not have full G2 holonomy. Its holonomy group is larger, less restrictive, because the curvature can impart twists that are not purely within the exceptional G2 group. These spaces are far more numerous and easier to find in the mathematical landscape than the perfectly torsion-free ones. They represent the vast middle ground between generic, uninteresting shapes and the exquisite, rare jewels of full exceptional holonomy. And for building a cosmos that looks like ours, this middle ground is not a compromise, it is the essential workshop. Why would we ever step away from the perfect holonomy that guarantees supersymmetry? The answer lies in the need to stabilize the universe. Recall the problem of the moduli, those massless fields from the breathing modes of the shape. To give them mass and lock the geometry into one stable configuration, we must introduce fluxes, those background field strengths threaded through the internal dimensions. But here lies the tension. Turning on these fluxes does something profound. It typically introduces torsion into the G2 structure. The very act of weaving energy through the geometry stresses it, preventing the 3-form phi from remaining perfectly constant. This stress breaks some of the supersymmetry. We move from a compactification that preserves n equals 1 supersymmetry to one that preserves a smaller amount or even breaks it completely. This might sound like a step backward, but it is a necessary step forward. A universe with exact, unbroken supersymmetry at low energies would look very different from our own. We would have seen superpartner particles in our colliders by now. Furthermore, achieving a stable vacuum with a positive cosmological constant, the key feature of our accelerating expansion, almost always requires breaking some supersymmetry. The fluxes that generate torsion and help stabilize the moduli are the very tools that can also lift the vacuum energy to a small, positive value. So the path to realism is not a straight line to perfect geometric purity. It is a winding road through the more abundant terrain of G2 structures with torsion. In these spaces, we can turn on the necessary fluxes, stabilize the shape, break just the right amount of supersymmetry, and potentially find a pocket of the landscape where all the numbers, the cosmological constant, the particle masses, and the force strengths align into a window that allows for a complex, structured universe to exist. The search, therefore, expands. We are no longer hunting only for the handful of perfect G2 holonomy manifolds. We are exploring the much wider universe of 7-dimensional spaces that can support a G2 structure, even a stressed one, and asking how fluxes and torsion can work together to sculpt a realistic cosmic home from the mathematics of M-theory. This geometric quest for a realistic universe now faces a profound and sweeping new challenge. Across the world of theoretical physics, a bold initiative is reshaping how we think about the laws of nature, not by asking what is possible, but by asking what is forbidden. This is the Swampland program. Its core premise is revolutionary. Not every seemingly consistent, effective 4-dimensional theory can be consistently coupled to quantum gravity. Some theories, no matter how elegant or mathematically sound they appear, might reside in the swampland, a landscape of dead ends that quantum gravity simply will not allow. The theories that can be consistently completed are said to reside in the landscape. The goal of the program is to map the border between them, to find the universal principles that act as gatekeepers, separating viable theories from those doomed to inconsistency. This framework forces us to re-examine everything we build, including our most promising geometric constructions from G2 compactifications. The beautiful 4-dimensional theories we derive from these 7-dimensional shapes must now pass a new set of cosmic litmus tests. They must not fall into the swampland. This brings us to a set of powerful, if still conjectural, principles known as the swampland conjectures. These are proposed rules believed to govern any effective theory that can truly emerge from a consistent theory of quantum gravity like string theory or M-theory. One of the most influential of these is the distance conjecture. In simple terms, it states that as you move an infinite distance in the space of scalar field values, like the moduli fields from our G2 manifold, an infinite tower of new particles must become exponentially light and appear in the theory. These are not random particles. They are typically the vibrational modes of strings or wrapped brains, whose masses depend on the moduli. Imagine you are tuning one of the geometric dials of the hidden space, say, making one of its internal cycles larger and larger. According to this conjecture, if you turn that dial forever, you do not just get a bland, scaled-up version of the same physics. Instead, the theory undergoes a radical transformation. A whole spectrum of previously massive, hidden states, perhaps entire Kaluza-Klein towers from the extra dimensions, suddenly collapse to near zero mass, flooding the low-energy world and completely changing the rules of the game. The old effective theory breaks down and a new one takes its place. This has a direct and dramatic implication for the geometry of G2 manifolds. The moduli fields from such a compactification live on a complicated geometric space of their own called the moduli space. Each point on this abstract landscape represents a specific, deformed version of the 7-dimensional shape. the distance conjecture makes a sharp prediction about the topography of this moduli space. It suggests that as you travel out to the boundaries of this space, as the geometry is stretched or shrunk in extreme ways, the physics must undergo this dramatic transition involving light towers of states. For a G2 compactification to be consistent, to truly be in the landscape and not the swampland, the mathematics of its moduli space must naturally accommodate this phenomenon. The geometry of the seven-dimensional shape must be such that when its moduli are pushed to their limits, there is a natural geometric reason for an infinite tower of wrapped branes or string modes to become massless. This often happens at boundaries where the manifold degenerates, developing a singularity or stretching out an infinitely long tube. The conjecture provides a powerful filter. It tells model builders that they cannot simply pick any point in moduli space and declare it our vacuum. The viable, stable vacua are likely to be special points, not in the deep interior where all moduli are finite and of order 1, but perhaps near certain boundaries where the effects predicted by the distance conjecture are under control and can be balanced against other effects like fluxes to produce a small cosmological constant. This shifts the strategy for finding realistic models. We are no longer just looking for any stabilized G2 vacuum. We are now searching for those that naturally sit at locations in moduli space consistent with the swampland criteria. The conjectures act as a guide pointing toward the kinds of geometric features, like specific types of singularities or extreme hierarchies in cycle sizes, that a viable hidden shape should possess. In this light, the pursuit of G2 geometry becomes a two-way street. We use the geometry to derive four-dimensional physics, and we use the swampland principles, born from deep quantum gravitational consistency, to constrain what the allowed geometry can be. It is a dialogue between the beauty of exceptional holonomy and the harsh, unforgiving rules of quantum gravity, a dialogue that is steadily refining our vision of the one perfect shape that could be our cosmic home. The sheer number of possibilities is both the great promise and the profound puzzle. If the landscape of vacua from G2 compactifications is as vast as it seems, it offers a potential answer to the most perplexing fine-tuning problems in physics. Why is the cosmological constant so small? Why are the forces the precise strengths they are? The optimistic view suggests that within this nearly infinite cosmic catalogue, there will exist at least a few rare entries where all these numbers align by chance to allow for stars, planets, and life. We would not need a single, divinely tuned equation, just the statistical inevitability of a multiverse with enough lottery tickets. This is the landscape paradigm at its most powerful, using geometric abundance to explain apparent coincidence. Yet, this very abundance casts a long shadow of doubt. Critics point out that not every mathematically possible vacuum is physically viable. The swampland conjectures act as a ruthless editor, potentially discarding entire libraries of these constructions for failing to meet the non-negotiable criteria of quantum gravity. A G2 compactification that looks perfect on paper might, upon deeper inspection, violate the distance conjecture or another fundamental principle, condemning it to inconsistency. It might be a beautiful mirage in the mathematical desert, not a real oasis. Furthermore, even among the vacua that survived this first cut, the vast majority could be dynamically unstable. They might represent shallow dips in the potential energy landscape, from which the universe could easily quantum tunnel to a different, perhaps catastrophic state. Or they might fail to properly stabilize all the moduli, leaving ghostly massless fields that would have already been detected. The fear is that the landscape of truly stable, consistent, and phenomenologically viable vacua might be far smaller than we hope, perhaps even empty. This tension defines the current frontier of research. It is no longer enough to simply construct a G2 manifold and derive its four-dimensional physics. The new, more demanding task is to rigorously audit each candidate. teams of theorists are now working to systematically check proposed stabilized vacua against the swampland criteria, using advanced numerical simulations on supercomputers to trace the intricate potential energy landscapes and search for deep, stable minima. They are asking for each promising point in moduli space: does it truly resist decay? Does it naturally accommodate the required towers of light states at its boundaries? The goal is to map the narrow, viable path through this treacherous terrain, separating the true landscape from the surrounding swamp. This is not merely academic housekeeping. It is a fundamental investigation into whether the universe's apparent fine-tuning is a solvable puzzle within our geometric framework, or a sign that we are still missing a deeper, more selective principle. The journey through the exceptional geometry of G2 manifolds has brought us to a precipice of understanding, where the next step requires not just building new shapes, but learning the ultimate rules of what can be built at all. The allure of G2 geometry is not merely physical, it is profoundly mathematical. This shape's exceptional nature connects it to one of the most exotic and beautiful structures in all of mathematics, the octonions. You are likely familiar with the real numbers, the line we use for everyday counting. Then come the complex numbers, which add the imaginary unit, the square root of -1, giving us a two-dimensional plane and the foundation for much of modern physics and engineering. Beyond that lie the quaternions, a four-dimensional system that famously describes rotations in three-dimensional space, used in computer graphics and spacecraft control. And then, at the peak of this hierarchy, sit the octonions, an eight-dimensional number system that is the largest of the norm division algebras. They are strange and wondrous, possessing a property called non-associativity, meaning that how you group numbers in multiplication matters in a fundamental way. This makes them notoriously difficult to work with, but also gives them a unique, almost magical structure. The exceptional Lie group G2 has a deep and special relationship with the octonions. In fact, G2 can be understood precisely as the group of symmetries that preserves the algebraic structure of the octonions. This is not a coincidence, it is a clue written into the fabric of mathematics itself. The special three-form that defines a G2 manifold, that phi field we discussed, can be constructed directly from the multiplication rules of the octonions. So when we study a seven-dimensional space with G2 holonomy, we are, in a very real sense, exploring a geometric universe whose core symmetry is dictated by the most exceptional number system we know. This connection elevates the pursuit from a technical exercise to a search for a deeper harmony between algebra and geometry. It suggests that the hidden dimensions, if shaped by G2, are not just curled up, but are curled up according to the pristine logic of the octonions. This mathematical pedigree alone makes these manifolds objects of intense fascination, independent of any application to physics. For pure mathematicians, G2 geometry represents a frontier in differential geometry, a testing ground for some of the most powerful techniques in analysis and topology. The central equation that defines a torsion-free G2 structure is a highly non-linear partial differential equation. Solving it, or even proving solutions exist, pushes the boundaries of what we know about solving equations on curved spaces. Each new construction, like those by Dominic Joyce, is a triumph that often invents new mathematical methods along the way. The study of these manifolds forces advances in understanding singularities, how to resolve them, and how to glue smooth pieces together into a coherent whole. It drives progress in gauge theory and the analysis of moduli spaces, the abstract landscapes where all possible deformations of a shape live. Topologists are captivated by the constraints that G2 holonomy imposes on the underlying shape of the manifold, restricting the kinds of holes and handles it can have. This pure mathematical journey is a virtuous cycle. The challenges posed by physics motivate new questions in geometry, and the resulting mathematical breakthroughs, in turn, open new pathways for physicists to build better models of reality. Whether one is drawn by the siren call of a unified theory or the silent beauty of an exceptional symmetry, the G2 manifold stands as a monument to human curiosity, a seven-dimensional sculpture where the most advanced questions of our time are being carved into shape. These open questions form a map for the next generation of explorers. The frontier of G2 research is not a single, distant peak, but a sprawling, interconnected range of challenges, each one a gateway to a deeper understanding of reality. First and foremost, we need more concrete examples. While existence proofs and numerical approximations are vital, the community urgently seeks explicit constructions of compact G2 manifolds with very specific phenomenological properties. We are no longer just hunting for any exceptional shape. We are looking for the ones that naturally produce, from their singularities and cycles, the exact gauge groups and matter representations of the standard model. Imagine searching through a warehouse of intricate seven-dimensional sculptures, not just for beauty, but for one that, when held to the light, casts a shadow in the precise shape of our universe's particle zoo. This requires moving beyond general existence to detailed engineered geometry. A parallel and equally daunting challenge is achieving full moduli stabilization in a controlled, explicit setting. We understand the theoretical tools, fluxes, and non-perturbative effects, but weaving them together into a complete, stable vacuum within a specific G2 manifold is a monumental task of calculation and consistency. It is the difference between knowing that a chair can be built and actually assembling one that will hold weight without collapsing. Researchers are using supercomputers to simulate these intricate potentials, searching for those rare, deep wells where every modulus is firmly trapped, giving us a stable four-dimensional universe with a small cosmological constant. Alongside this, there is the critical work of computation. To make real contact with observable physics, we must be able to calculate the Yukawa couplings. These are the numbers that determine how strongly matter particles, like quarks and electrons, interact with the Higgs field, which in turn sets their masses. In a G2 compactification, these couplings are not arbitrary inputs. They are derived from overlap integrals of wave functions localized on different cycles within the manifold. Computing them requires the full numerical power of the approximated metric, a Herculean task that is only now becoming feasible. Each successful calculation transforms an abstract geometric model into a theory that makes concrete predictions about particle masses and mixing angles. Finally, there is a foundational mathematical quest to rigorously connect singular G2 spaces to chiral gauge theories. We have compelling physical arguments that conical singularities give rise to forces and matter, but turning those arguments into airtight mathematical theorems is essential. This means proving with full mathematical rigor that the process of resolving these singularities in a G2 context inevitably produces a four-dimensional effective theory with chiral fermions and the correct gauge structure. It is about building an unshakable bridge between the language of differential geometry and the language of quantum field theory. Each of these open problems is a thread in a larger tapestry. Solving them would not just answer a technical question, it would demonstrate that the universe we inhabit could genuinely be a natural and inevitable consequence of geometry singing in seven hidden dimensions, with a melody composed in the exceptional key of G2. The journey from an abstract symmetry on a page to the potential architecture of our universe is a testament to human curiosity. We began with a puzzle, the search for a single law of nature, and followed a trail of clues that led us into the hidden folds of geometry. The concept of supersymmetry demanded a specific kind of compact space, and the mathematics of holonomy provided the fingerprint we needed to identify it. That fingerprint pointed unequivocally to one of the rarest and most exquisite shapes in all of mathematics, the G2 manifold. This seven-dimensional space with its exceptional holonomy is not merely a mathematician's daydream. It represents a critical, tangible intersection where the deepest ideas from geometry meet the most fundamental questions in physics. Its perfectly constrained curvature is the proposed foundation upon which a stable, supersymmetric version of our reality could be built, where every particle and force emerges from the silent song of curled-up dimensions. The path is undeniably challenging, filled with open questions about moduli stabilization, explicit construction, and the stringent new rules of the swampland. Yet, each challenge sharpens the quest, transforming it from speculative fantasy into a rigorous engineering project at the scale of creation. This entire exploration stands as a powerful reminder of a beautiful and unexpected truth. The most profound advances in our understanding of the physical world often spring from the purest pursuits of the mind. The study of exceptional holonomy began as an investigation into the possible symmetries of curved spaces, a question of sheer mathematical beauty. It was only later that physicists discovered this same rarefied geometry held the key to hiding supersymmetry and potentially unifying all of nature's forces. The story of G2 manifolds exemplifies this deep, mysterious dialogue between abstract thought and concrete reality. It shows that the universe may indeed be written in the language of mathematics, and sometimes that language speaks in the refined, exceptional dialect of seven-dimensional shapes. If this fusion of geometry and physics has sparked your imagination, the journey is just beginning. We encourage you to explore further, to delve into the worlds of string theory, Calabi-Yau manifolds, and the ongoing search for a theory of everything. The cosmos is waiting to be read, and its most fundamental chapters may be written in a geometry we are only now learning to see.